So this brings me to the last part of my lecture, which is very brief, very, I'm not going to go into very much detail, but I want you to I wanted you to know that there is also work on thresholdizing quantum resistant schemes, since we know that dice-log and RSA are not resistant against quantum computing. So the first is a work that appeared a couple of years ago at Crypto, which shows that if we can build a threshold fully homomorphic encryption, then we can build what we call a universal thresholdizer. I thought when Dan came out with this word was, genius. It's basically a compiler that takes any cryptographic schemes and builds a threshold version of it, which what's really interesting is non-interactive. It thresholdizes the cryptographic scheme in a single round. And this work is very highly related to MPC computation in one round when you have a distributed fully homomorphic encryption. And in fact, in my mind, this is not just about thresholdizing cryptographic schemes, but it's about doing general MPC when you have threshold fully homomorphic encryption. So let's start with a candidate fully homomorphic encryption, for example, the Gentry Sahai Waters scheme, which is based on learning with errors. So in this scheme, the secret key is a vector of size L of integers modulo Q. And a ciphertext is a matrix of size L times M into the same space ZQ. To decrypt, take a column. So the matrix represents M bits. You take a column of the matrix, and you do the inner product with the secret key. And if the result of this inner product is small, then the plain text is 0. And if otherwise, the plain text is 1. And small is a parameter of the scheme, which depends on the security of your LWE problem. So you can do an N out of N scheme pretty, I wouldn't say simple, but it's not that complicated either. You take your vector and you split it into N out of N additive shares. And then what you're going to do, a party I will compute locally the inner product of this share with the ciphertext, okay? Now, to avoid revealing information about a secret share, the party will add a small amount of noise to this inner product, okay? This is some sort of smoothing. In some of the literature, I think this is called smoothing. So now we have this partial decryption right here. And then, so we add this noise because we want to hide your secret share. And then, because the noise is small, when you add all the shares, the noise doesn't grow too much. And so the decryption test will still work. There's enough slack there in your parameters that this added noise is still going to give you the same decryption, okay? So D is not going to be that far from the sum of the DIs. And so you can, the correctness of your decryption will still work, okay? Any questions so far? So, and this was...
No questions.
No questions. This was known before we did this work. So what is the problem with doing this with threshold? That if we split SK with Shamir, then, and we do this thing in which each party, it's basically very similar to the problem that we were having with RSA. It's still the Lagrangians, because now when we interpolate with the Lagrangians, with RSA, we had the problems that the Lagrangians had fractions, and we couldn't divide. Here, the problem is that the Lagrangians are going to multiply the noise too. And that's going to make the noise of this linear combination much bigger. And it's going to bring this value far from D. And so your decryption is not going to work anymore. So what you're reconstructing is basically useless. Okay, so is it clear what the issue is with doing Shamir, right? So, okay, so we propose two solutions. The first one is don't do Shamir. There's plenty of secret sharings out there in the literature that are different than Shamirs. And in particular, what we want is a linear secret sharing. Why do we want it linear? Because we want the ability to compute the inner product efficiently from the shares, right? So by linear, I mean that you can compute a linear function over the shares. But the reconstruction involves only binary coefficients. Now, if that's the case, then when we reconstruct, because these BIs are linear, the noise is still going to stay small. And because it's still going to stay small, this linear combination is going to be close to the value that you would get in the centralized case, and so decryption still works. Okay? The question is, how expressive are these linear secret sharing with binary coefficients? Turns out that they are quite expressive. And I mean, this is something that surprised me. And in particular, they include threshold access structures. So we can do N out of T, T out of N, and more with this 0-1 LSSS. The drawback is that if you, in a way, tie your hands and not use Shamir and use this kind of combinatorial constructions, the size of the shares for the players grow. In particular, for N players, each player has to hold something on the order of N to the fourth shares. But we can do it. The other option is an option that is very similar to this factorial trick that Shoup did for threshold RSA, is that we are going to use Shamir. And then the first thing that we're going to do, we're going to remove the denominators, and with the usual trick of multiplying by n factorial, and then we just choose our parameters so that we can accommodate this noise growth. What is the disadvantage there? Now that our parameters are going to get, if LWE parameters are already big to begin with, they're going to get even bigger. And even more troublesome is that now the issues of the centralized key are dependent on N. So it's almost like this encryption scheme that I put out there for people to use, people will know that it's a scheme that pertains to N parties. You know, it's not just the internal computation that depends on N, it's also the encryption operation is going to depend on N, which is something that we don't want. And bear with that thought for a minute, because we're going to be able to address it. But either way, we have it. We have a threshold FHE, neither of them incredibly efficient, but one of them with using this binary linear secret sharing, or with growing the noise parameters using Shamir. Once we have this threshold FHE, we can build a universal thresholdizer, which is a pretty standard notion in that basically we want to use this threshold FHE to do non-interactive MPC. So here's the idea. So you have a secret K, and your setup outputs a shares of K and a verification key. So you want to think of this is the secret key of your centralized cryptographic schemes. So a dealer is going to share them and is going to put out some commitments to all of this. And we're going to use this to verify that the players are behaving correctly. Now, once you have done this, what you're going to do, you have a circuit. This is your cryptographic algorithm. Think of it as a signature, which input X, which is your message, for example, and the share of your secret key. What you're going to locally do, this requires no communication. It outputs a partial evaluation of the circuit. Then there's a verification algorithm that verifies that this partial evaluation is correct. So you want to think of this partial evaluation that it includes some sort of proof of correctness. And then, given t+1 correct partial evaluations, you should be able to compute the entire value of the circuit, again, locally. So there is just one round of computation, which is one round of communication, which is every party broadcasts this value yi there. And how do you do this? It's basically a combination of threshold FHE with non-interactive zero-knowledge proofs. So the setup, you take what is the share of each party? The share of each party is the share of the threshold FHE. And if this is the secret key of your cryptographic scheme, you're going to encrypt it with the FHE, and you're going to commit to all this SAK. And this will give you the verification key. Now, on input a circuit C, X, VK, and share SAK, you can evaluate FA of the circuit K of X using the homomorphism of A. So this eval does nothing. The first step of the eval just evaluates C on X and K using the homomorphism of FHE. And then your local evaluation is produced as the partial decryption of this encrypted computation, plus a zero knowledge of correctness, an interactive zero knowledge of correctness, that you're actually using the correct key, the correct SK, and so on. And then the verification checks the NISC, and the reconstruction uses the reconstruction procedure of the threshold FHE to decrypt the value. Right? So once you have this very powerful threshold FHE, there's nothing here really that says that C has to be a cryptographic function. It could be any function. So what are the application? I just say, if K is the secret key of a cryptographic scheme, and C is, say, your signature, you obtain a one-round threshold version for any scheme. By the way, one interesting application is the compression of the non-succinct Shamir-based threshold FHE that I showed earlier, because that scheme had parameters that grow with n, but you can feed this, you can use this non-succinct threshold FHE to build a non-succinct universal thresholdizer. But then you can use this non-succinct universal thresholdizer to thresholdize a centralized succinct FHE. So now what people see from the outside is not dependent on n anymore, right? And all the computation that depends on n gets back inside the network of players. This reminds me a lot of the boosting step of FHE, right? After a while, you sort of bring it back. You bring back the noise under control. And here, sort of, we're using this noise that grew up by doing the threshold. We bring it back through the same procedure. So I think this is, yeah, I think I'm done with that with lattices. If there are any questions.
Yes, there is one question.
Yeah, go ahead.
A few slides back about growing the parameters. The question is, how big do the LWE parameters become? And does it become infeasible to compute FHE operations?
No, it doesn't. Your parameters grow in by n log n, right? Because you have to accommodate this n factorial. So they grow, but it doesn't become infeasible. It's just your Q and your L and your M have to grow by n log n bits. Okay. So large N, you maybe want to think about it, right?
Okay. No more questions.
Okay. Okay, so the last, I don't know, 10 minutes of this lecture, I wanted to talk to you about isogenies. That's because the last few months I've been trying to learn about isogenies. So I'm going to say, if there are people who are isogenies experts in the audience, I ask your forgiveness. I'm going to give a very, very simplified version of what isogenies are based on my very weak understanding of them. But I understood enough to know what are the problems when you want to thresholdize or distribute this computations. So let me give you a very brief one slide introduction about what isogenies are. So we have a set, a function called E. In most of these instantiations, E is a set of elliptic curves, which is endowed with a group action G. What do I mean by that? Simply is that if you take an element G in the group and a curve E in the set E, there's an operation that takes the group and the curve and gives you another curve in the set E, okay? So over this set, over this homogeneous space, we have our problems, which is given two curves, E and E prime, find the group element that maps E into E prime. This is the equivalent of the discrete log problem in the space. The other problem is given E and E prime, such that E prime is E acted upon by G, you want to find, and then given another curve F, you want to find F prime, which is G acting on F. And this, you can see, is the equivalent of the computational Diffie-Hellman problem. Okay? So those are the hard problems in the space. The main difference with cyclic groups and discrete log is that basically there is no structure on the set E, which is so if I give you two curves, it's not like you can multiply them together or something like that, right? So this is the source of the conjecture quantum hardness of these two problems. And in isogeny-based instantiation, as I was saying, E is the set of elliptic curves. And basically, the operation brings you from one curve to another. And you can take this curve, take this curve and this curve and multiply them. And there is no multiplication operation among the curves, right? Okay, so any questions so far? So this is the one slide about isogenies and
no questions.
Yeah. So, and here is how you build a signature scheme. Is basically a riff on Schnorr's. You take a base curve. We're going to assume that our group G is ZQ with the addition operation. Okay. So Alice knows a group G such that F, so basically Alice knows the quote unquote discrete log of F respect to E. And she wants to prove that she knows G. So she runs the following protocol. Remember this is like Schnorr, so she's going to send F prime, which is E raised, the equivalent of raising E to a random value A. Then the verifier sends a bit B, and if B is 0, Alice answers with A, and the verifier checks that F prime was really computed as A times C, and if bit is 1, Alice answers with A G inverse, which really should be A minus G. And the verifier checks that if you take F and you apply C, then you get F prime, because the G cancels and you're left with A. This is exactly Schnorr with binary challenges adapted to the quote-unquote Dasquille log problem in isogenies. This proof can be turned into a signature scheme via the Fiat-Shamir heuristics, where the challenge is chosen as the hash of everything, including the message. You have to repeat it, obviously, several times, because this basic protocol has soundness and half. So, okay, so how do you thresholdize this? So this is, on this side, I have the signature scheme. So let's assume that the dealer has shared the secret key. Let's not even think about the KG. We'll talk about that in a minute. But let's assume that the dealer has shared G via Shamir among the n parties with threshold T. So when T plus 1 parties want to sign, the first thing that they do, they can map their shares to additive ones. Remember, if you know your T plus 1 things, you can just scale them by their proper Lagrangian. And then each party selects a random value AI, and they perform this thing distributedly. But the first thing that they have to do is compute this F prime, right? Which is A times C. So if each guy has AI, the only way that we know how to compute A times C is to apply A repeatedly. So the first guy applies A1, then the second guy applies A2 to the result of the first guy, and so on. And the last guy will be F prime would be A times E, where A is the sum of the AI. Okay, so one thing that I didn't say in the previous slides is that if you apply two groups element in the in succession, then you're going to get the sum of the group elements. That's where there's this sort of homomorphism property of the equation. But you can only do this sequentially, because if I apply A1 and you apply A2, we end up in two different curves, and there's no operations in the curves that would allow us to combine A1 and A2 after we apply them in parallel, which we have with Dasquille log, right? So then you can, once you finish this n round computation, you compute the challenge B hashing, and then you just output. Here's a bunch of confusion because it's additive notation. This inverse is really minor, so I ended up not fixing the slides. And then you're done. And C is the sum of the CIs, right? So the main issue with this protocol, is the sequential computation, because you cannot combine two separate isogeny computations done in parallel, because you're going to end up into different curves. What you can do is, I do my first curve, and then you act on that curve, and then the next guy acts on the second curve, and so on. Okay? So this protocol right here is, they described it just with a dealer and with honest but curious case. So then, okay, so how do we, and then we have a dealer, right? But the reality is that this protocol right here in the middle can also be thought as a DKG, right? Because they're basically generating a AI, a random value A, and the mapping of the curve under the combination of the A's. So this generation of these nonce can also be used as a DKG if you want. You have to sort of somehow make sure that this additive gets mapped into shares, but that's okay. It's sort of like, it's basically the equivalent of a Feldman BSS, with the main crucial difference that you have to do things in sequential rounds rather than in parallel, the way Feldman does it. As in Frost, we use the same Schnorr-like zero knowledge proof to prove that we know what we're contributing, and this will give us malicious security with abort. Okay, so the ideas are pretty much the same. We're sort of leveraging this informal connection between task log and isogenies with the big caveat that everything that is in parallel with task logs becomes sequentials with isogenies. Okay, and then finally, there's the last paper from last year sort of dealt with the issue of how do we get a robust DKG with guaranteed termination and fairness and uniform distribution so that we can do proof by simulation. And in this, we need to notice that the most important thing here is that in the setting of isogenies, there is no equivalent of a Pedersen VSS, right? Which is what we used to get this fair, robust DKG. Why? Because again, Pedersen is really based on the fact that I do a sharing of my secret and a sharing of a random value, and then I multiply them together. And there is no way to multiply these two things together in an isogeny setting, right? So there is no way to do this information theoretic Pedersen thing. So what they did was create this non-malleable VSS. I'm still wrapping my head around this paper. Using zero knowledge proofs. And this gives you the non-malleable and recoverable properties that, if you remember from yesterday, we talked about are needed to get this joint VSS computation work so that we can always have the protocol terminate with the right target public key. However, the combination of the secret keys into a unique public key remains inherently sequential due to the lack of structure of the isogenies. And a student of mine and I have been sort of looking at this for a while, and then we realized, oh my God, this is exactly why it's quantum resistant. If we were able to do this, we would probably be able to adapt the Shor quantum algorithm to work for this too. So, and actually that would be an interesting question to ask. If you were able to do something like a Pedersen VSS on isogenies, would that mean that isogenies are not quantum resistant, right? So I'm done with the technical material, and I think I'm also done out of time, but allow me one slide, again, with my target audience in mind of graduate students who are getting into research. Here is a very non-exhaustive list of open problems. The first one is a truly scalable DKG that requires less than quadratic communication. Can we use recent advances in SNARKs and, or at least what I mean by less than quadratic, at least the public communication that everybody has to look at, because sometimes that's what goes into a blockchain. So you want to make that as small as possible. Can we use recent advances in SNARKs to do that? Can I just put a very small proof that everything is correct? So in theory, we can. The question is, can we actually build it, right? Lots of these problems have a theoretical component, but they also have a engineering optimization component that are really both fascinating in each side, right? Better proofs. One thing that I didn't mention was that the threshold DSA protocol that I showed you yesterday has a proof in the universal composability framework. I am not aware of a UC proof for Schnorr. The proof that Frost has does have a proof for concurrent executions of Frost, but not a proof for UC. I don't think it would be too difficult to get it for Frost or to modify Frost in a way that wouldn't lose much of the efficiency beauty of Frost and get a full UC proof. So that, in my mind, that's kind of a low-hanging fruit. People who have familiarity with UC proofs may want to look at that. So we have this really beautiful result about, FHE-based universal thresholdizer, but is it theoretical? Is it practical? FHE has been making great strides, and at what point it pays off to say, forget trying to build threshold DSA from scratch. I'm just going to, or the next threshold scheme, I'm just going to call my universal thresholdizer, maybe tailor it in some way and get my threshold, my one-round threshold version. And by the way, a similar question can be made for MPC, right? MPC has been making greater strides than FHE. At some point, and I'm sort of killing my own research area in a way, at some point it may be worth, and this is actually a question that everybody should ask when they design a threshold scheme, what am I gaining with respect to a general MPC solution? And finally, can we have threshold isogeny-based schemes that don't have this sequential rounds structure? And as I said, I believe that it might be inherent, in which case can we prove that if there is a constant round threshold isogeny scheme, then it has to be necessarily not quantum resistant, right? Then you're basically going back to Daskel log or something like that. So those are the questions that I'm thinking of. So those are the questions that they're not the only open question in the area, and there's plenty more. And I think this is the end for me.
Thank you, Rosario. Thank you for this wonderful series of lectures on a very timely topic of threshold signatures, which enjoys a lot of interest now, and there's still a lot to do, as you said in your last slide.